Welcome to Life with David. I'm David, and today I'm changing my RP2040 focus to programming in assembly language. I guess I'm a glutton for punishment, but I cut my teeth on 6502 machine language, and I've always enjoyed dealing with individual bits and bytes. This is the first time I've done any low-level work with ARM processors, so it's going to be a learning experience. So why don't you join me as we start our adventures in bare metal programming? Since the dawn of the computer age, massive effort has been made to make programming accessible to all. To that end, programming languages such as Fortran, COBOL, BASIC, and many more were developed. These higher-level languages, along with cheaper and plentiful memory, allowed tremendous amounts of code to be created quickly by many people. As a result, we now have a digital-based society including smart devices, unlimited communication, and artificial intelligence. Lots of memory is a key to the success of high-level languages. There's a lot of memory overhead that goes along with using languages like C, C++, or Python. Even with a simple Blink program, C can consume more than 5 times the memory than assembly language. It also takes time to chug through all that memory, so high-level code is much slower than the equivalent low-level code. But remember, it's all a trade-off. Code is much easier to create with high-level languages, so increased memory usage is just a cost of doing business. However, for lean, time-critical code, nothing beats low-level languages. The lowest is machine language, where the programmer enters the individual numbers that control the processor. This is how the very first computers were programmed and how I programmed my 6502 back in 1976. Assembly language was a huge step forward since it let the computer keep track of all the crap like offsets, branches, and opcodes while keeping the program lean and fast. That's what we're going to be using for our bare metal adventures. Why is it called bare metal? Well, we're going to be interacting directly with the registers and memory locations. There's no high-level language to insulate us from what's going on. It's stripped down to the lowest level. For those who haven't experienced low-level programming before, I'll do a quick overview of microprocessors in general and the ARM Cortex-M0 Plus in particular. Don't get overwhelmed. We'll step through this in more detail later. Microprocessors have several types of data storage. These include registers, random access memory, the stack, and peripheral. Registers are a small number of very fast and specialized locations close to the processor where data can be moved very quickly. Random access memory has much larger data and program storage capacity, but is slower than the registers. The stack is usually a subset of RAM with specialized instructions that allow for faster operation. And peripheral is a set of storage locations where data can be shared between the processor and the outside world. There are many other types of memory, including pipeline and cache, but we won't talk about those at this time. The arithmetic logic unit, instruction decode, and control sections of the processor read machine language instructions and perform data manipulation in and out of the various types of memory. For now, we're going to concentrate on creating and running those machine language instructions. I think this is a good time to talk about the RP2040 ARM processors and the associated microcontroller-related peripherals. As always, my starting point is the RP2040 datasheet. This is an extremely well-written document that provides all the data needed to understand the microcontroller functions of the chip. The ARM Cortex-M0 Plus user manual and the ARM version 6 architecture manual are also extremely useful. I'll put links to all those in the description below. Please don't get overwhelmed with the information that follows. This is just an overview. We'll go into more detail later. The RP2040 has a pair of ARM 32-bit Cortex-M0 Plus processors. Each processor has 13 general-purpose registers for temporary data storage and 3 specialized registers that include the stack pointer, link register, and program counter. Another set of 3 registers, collectively called the program status register, combines the application, interrupt, and execution program status. The instruction decode section parses the instructions that make up the program. It then uses microcode to control how data is moved around between the register's memory and the arithmetic logic unit, or ALU. The ALU performs bitwise operations on 1 or 2 words of data and performs comparison operations. The results are sent to the register's memory and/or status flags in the application program status register. Now let's talk about the ARM instructions. There are 4 broad categories of instructions: memory access, general data processing, branch and control, and miscellaneous. The Cortex-M0 Plus uses what ARM has named the thumb instruction set, which consists of mostly 16-bit instructions with a few 32-bit instructions thrown in. Thumb technology increases the instruction density, or number of instructions that can be stored in a fixed amount of memory, compared to ARM 32-bit instructions, but at the cost of fewer instructions and effectively restricting register access to general-purpose registers 0 through 7 for all but a few special instructions. I'll use the free ARM assembly emulator, CPU, later to demonstrate some of the basic commands. I'll put a link in the description below. Even though this emulator is not for the exact ARM version as the RP2040, it'll still give us a good understanding of how the processor works. Let's start with the memory operations instructions. Here's a little program that demonstrates some of the basic commands. The word size of the Cortex-M0 Plus processor is 32 bits, so the registers and memory locations are represented by 8 hexadecimal digits. As I mentioned earlier, the registers are very close to the processor, so access is very fast. To write fast programs, we should use the registers as much as possible. One way is to use the move instruction. This instruction can load an immediate byte into a destination register or load a destination register with the contents of another register. The syntax for this instruction is similar to many other instructions where the destination register is listed first, followed by the data source. An immediate byte is identified by using a hashtag in front of the number. In the first instruction, we'll move 255 decimal into register 0, and in the second instruction, we move 64 decimal into register 1. We can communicate with register or peripherals using the store register or load register instructions. Here, using the str instruction, we'll store the value of register 0, which is 255 decimal, into the address location contained in register 1, which is 64 decimal. Conversely, using the LDR instruction, we'll load register 3 with the data stored in memory whose address location is stored in register 1, which is 64 decimal. We can also use offset and labels. We'll dive into those in the future. We'll round out memory instructions by accessing the stack with push and pop. First, we'll push register 3 to the stack, and then we'll pop the value off and put it in register 4. Before I compile the program, I'd like to mention the 2 lines at the start. In this line, we set a label for the start of our program. However, these labels are only recognized within our program. Our program will be running in conjunction with some operating system, and we need to tell the system where the program is. The statement .global does just this. Although this emulator adds these 2 lines automatically, we'll have to manually add them to the scripts we write for our RP2040 programs. I'll compile and load our little program. In the disassembly view, we can see the 6 instructions and the machine language program that was generated. If we go to the memory view, we can see that the program was placed into memory starting at 0000. Let's step through this program. First, you can see that register 0, which was originally loaded with 0, now contains 255 decimal, or FF hex. The next instruction enters a 64 decimal, or 40 hex, into register 1. The third instruction takes the data from register 0, which is FF hex, and places it into the memory location whose address is held in register 1, which is 40 hex. The LDR instruction reads the memory location whose address is stored in register 1, which is 40 hex, and stores the data, which is FF hex, to register 3. The push instruction stores the value of register 3, which is FF hex, to the next available location on the stack, which is location FF, 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 FC hex. Finally, we'll pop that value off the stack and into register 4. Along with the label that starts the program, we'll also use labels to jump to different places in the code, just like any other language. We move from one section of code to another using branch instructions. There are a whole series of conditional and unconditional branches that can control the flow of the program based on the status of the negative, 0, carry, and overflow flags. Here's a little program that demonstrates how we can use conditional, unconditional, and subtraction to add a delay. First, we start with the label loop. I'll move 3 into register 3 and then jump to a subroutine called delay using the BL instruction. This saves the location of where the program will resume operations after the subroutine is complete to the link register. Here we subtract 1 from register 3, and using the S suffix, we update the negative, 0, carry, and overflow flags. Then we use a BNE to branch back to the beginning of the delay loop if the result of the subtraction was not 0. When the result finally gets to 0, we'll jump through the BNE instruction to the branch indirect instruction, which will use the link register to take us back to where we were before the delay subroutine was called. As we step through the program, you can see how register 3 counts down to 0. When the result is 0, the program execution then returns to program counter 8, and we do it all again. I went through this pretty quickly, but now we know the basic instructions we'll need to do a bare metal blink of the Raspberry Pi Pico's LED. I plan on covering assembly programming in a little more detail in future videos, but if you want to get a head start, I'll put a link to a good video that uses this same emulator to teach ARM assembly. Let's put together an assembly language program to blink the LED of the Raspberry Pi Pico. Spoiler alert, I won't have time to show you how to compile and install this program in this video. That's a whole process that deserves its own video, which I'll create shortly. I'm using the GNU assembler for ARM. I chose it because I think it's the most available assembler, and it's part of the current Raspberry Pi recommended toolchain for both Windows and Linux systems. The syntax between different assemblers varies, and what I type here may create errors for other assemblers. I'm using Notepad++ as my editor. Although it's not perfect, I find it's helpful to add the ASM for ARM GNU language to Notepad++ since it helps a bit with format. To add the language, open Notepad++, click on the languages in the menu bar, and scroll down to the user-defined language and select Open User-Defined Language folder. This will give you the location to store the new language. In the address bar, right-click and select Copy Address as Text. Now go back to Languages and under User-Defined Language, select Notepad++ User-Defined Language Collection. This will open a GitHub page where people have submitted different language files. Scroll down about halfway to where it says, "Here is the URL list," and click on the link. Now scroll down to ASM for ARM GNU. Click on it and then click on the Raw button. The language will open as a text file. Right-click and select Save As. A Save dialog opens. Right-click on the address bar and select Paste. This will choose the address of the language folder you just copied. Press Return and select OK. Now restart Notepad++, open Languages again, and select GNU ARM from the drop-down menu. OK, back to the program. The RP2040 controls several peripherals using what is called the single-cycle input-output block, or SIO. This provides high-speed, low-latency access between the processors and many peripherals, including GPIO. SIO does not use the main system bus, but rather is implemented with a dedicated bus interface with each of the processor's I/O port. We'll access the I/O port registers directly to blink the Pico LED, which is located at GPIO 25. From this simple flow chart, we'll first write an appropriate bit to the output set register, execute a delay routine, and then write the same bit to the output clear register. After another delay, we return to the top and do it all over again. However, before we can write to the GPIO output registers, we need to connect the GPIO to the SIO using the GPIO function select register, and then enable the GPIO pad as an output. In a full bare metal application, we have to release the reset which is holding peripherals in a safe state before we can use GPIO. This chore is normally performed by the SDK. Since my goal is to eventually not use an SDK, I'll include this in our program also. The IO Bank 0 reset is controlled by bit 5 of the reset control register located at 4000C000 hex. We could clear that bit, but we would first have to read the bit mask, that exclusive OR the bit mask with the bit we want to change, and then write the bit mask back. That's actually a lot of work. An easier way is to use the RP2040 atomic registers. All you have to do is set the bit you want to change and write it to the appropriate set or clear register. The atomic registers do the rest for you. In our case, we'll write a 1 in bit 5 to the reset register address plus 3000 hex or 4000F000. Let's start writing the code. Start with .global start and the label start. I'll set up an area at the end of the program for our defined data after the label data. Here we can assign data values to variable names. The first one will be the address for the atomic register to clear the reset controller. Note the syntax. After the data label on a new line, type .equ, the name of the variable, in this case rstclr, and then the value to assign the variable, which is 4000F000 hex. Now use LDR to move rstclr into register 0. After the destination register, enter an equals sign followed by the name of the variable, in this case rstclr. Now we need to input the bitmap for clearing the reset controller for IO Bank 0. As you can see here, it's bit 5. Since that's represented by decimal value 32, we'll move the immediate value of 32 into register 1. I'll use the store command to store the contents of register 1 into the memory location whose address is held in register 0. This will clear the reset for IO Bank 0. But when? We need to verify that the reset has been cleared. We can query the reset done register, which is located at a base of 4000C000 hex plus an offset of 8. If bit 5 is a 1, then the reset has been cleared. Let's add a label RST at the beginning of this section. Then I'll assign the value 4000C000 to the variable RST base. I'll load that value into register 0 using the LDR instruction. Next, I'll read the value of the reset done register at a location at RST base plus an offset of 8. Then I'll use the move instruction to put 1 in bit 5 of register 2. To isolate the IO Bank 0 status bit, we will AND the contents of register 1 and 2 and put the results in register 1. This will set or clear the 0 flag, which we'll use to determine if the reset has been cleared. In some assemblers, we would need to use ANDS to set the flags. However, the GNU assembler just uses AND when using the ARM thumb instruction set. If the 0 flag was set, then the IO Bank reset has not been cleared and we'll branch back to the label RST and check it again. If the result was not 0, the result has been cleared and we can move on to the next section. Now we need to connect the SIO to GPIO25. We'll assign function 5 to the GPIO25 function select register, which is located at 400140cc hex. I'll assign that value to the variable CTRL and move it into register 0 using the LDR instruction. Then we'll move the number 5 into register 1. Using the STR command moves the 5 into the GPIO25 function register. Now we can access the SIO GPIO registers. Here we'll set up a bit mask to enable GPIO25. This is done by writing a 1 to the 25th bit and setting it to the GPIO output enable register. First, I'll set up the bit mask for GPIO25 by loading a 1 into register 1 and then shifting the register 1 left 25 bits. Next, I'll set up a variable SIO base and assign the value D0000000. Then I'll move that into register 0. Finally, I'll store the bit mask in the GPIO output enable register, which is D0000000 plus an offset of 36 decimal or 20 hex. Now we're ready to go with GPIO25. I'll add another label called LED loop. The bit mask for GPIO25 is already loaded in register 1, so we simply store it in the GPIO output value set register using the STR command with a base of D0000000 plus an offset of 20 decimal or 14 hex. This will turn the LED on. Now we have to add a delay. We'll use a subroutine called delay, which counts down from a really big number, about 16 million, until it reaches 0. I'll set up the variable bignum and give it the value of F00000 hex. Then I'll load that into register 3 before I use the branch with link instruction to enter the delay subroutine. The BL instruction saves the return point in the link register. The delay subroutine simply subtracts 1 from the value in register 3, stores the result back into register 3, and updates the status flag. As long as the result is not 0, the BNE instruction will jump back to the beginning of the delay subroutine. However, when the result is 0, the program will jump through the BNE instruction to the BX or branch indirect instruction using the address in the link register. This will return the program counter to the next instruction after it jumped to the subroutine. Now we do almost the same thing as when we turned the LED on, except we'll write the bit mask to the GPIO output value clear register. This will turn the LED off. Then we'll complete the delay subroutine, return, and then take an unconditional branch to the beginning of the LED loop and do it all again. That's it. We can blink the LED and we only use 50 bytes for the program and 20 for the data. That compares to over 2K bytes to do the same thing in C. This video is getting really long, so I don't have time to compile a link and load the program here. You can see that it does work, and I'll be uploading a video shortly on the procedure for getting this program into the Raspberry Pi Pico. Thanks for joining me today. I did a crash course in ARM assembly language and touched on some of the registers the RP2040 uses to control GPIO. This is the beginning of our bare metal adventures. Next time, I'll demonstrate how to load this program into the Pico. I'm planning on digging deeper into low-level programming in the future, so stay tuned. If you like this video, or you think someone else might, please give it a thumbs up. If not, give it a thumbs down. The more likes this video has, the more YouTube will recommend it to others. Also, please leave a comment or suggestion for things to do. I hope to do more of these videos, so please subscribe and click on the bell for notifications of new videos. Let's get together next time for another day in Life with David. See you soon!